is Toby. The video today will look a little different because I don't have my normal laptop that I use. It's in repair right now. But this week I have been learning about software complexity measures, and in particular I chose to dig a little deeper into something called the Halstead complexity measures. I did a little coding, a little research, a little coding, and I wanted to present my results, at least the ones I've gotten so far. So Halstead complexity measures, you can read about it on Wikipedia on this page here. It is a evaluation. It's a metric for a particular program or a programming project, which can be done via static analysis. So by static analysis, I mean writing a program that loops through the AST of a program, the abstract syntax tree, and it calculates certain things about it. And in this case, the Halstead complexity measure is based on these four numbers. And these four numbers are the number of distinct operators. I don't actually know how to pronounce this Greek letter. It looks like a little n with one of its legs longer than the other. I really don't know how to pronounce this, so I'm sorry. The number of distinct operators, the total number of operators, and the total number of operands. Sorry, it's operators versus operand, and then one version is the distinct number of those things, and then the other version is just the total of those things. And then out of these four numbers, you're supposed to be able to derive via equations these other measures, including the program vocabulary, which I really like the word vocabulary because it gives you an intuitive notion of like how much vocabulary you're required to know in order to read and understand this piece of program. Sort of the same way you can look at literature. The program length, there's also a calculated estimated program length. The volume of code, the difficulty of the code, which is supposed to measure how difficult the program is to write or understand, i.e. when you're doing a code review. This is of particular interest to me because I work on a software team, and the software team is consistently doing code reviews. And then finally, effort, which is supposed to be a measure that means how much effort it would have required to write that piece of code. Okay, so an example of that was accompanied, or this article is accompanied with this example written in the C programming language. And so examples of operators here are main. So main is actually seen as an operator as it is a function, and a function is a verb. So function names are actually considered operators. The open and closing of the parentheses, that is considered an operator. I actually don't know whether this means this one here, which is used as a grouping, or the parentheses that are used to surround the argument list. And I don't think my analyzer considers this grouping case to be a separate operator. So that's something. And this curly brackets, so this code block, it actually considers an operator, and I don't think I'm considering that as an operator either. So there's actually some differences between my analyzer and this one. But the operands are the variable names. So A, B, and C are operands. Average, So that's also a variable. So all variable names are operands. String literals are also operands. And I generalized that to say that like array literals and dictionary literals, I also call them unique operands. So, and this gives you a calculation. Oh, there's also the number of bugs delivered, which I actually didn't calculate because I don't know. I found that number to be highly dubious. Okay. There are other software metrics which I haven't gotten to. So, and perhaps in the future I can learn about those and present them to you as well. Okay. So I wrote a program, and I'll show you the GitHub page. I published it to GitHub if you're interested in looking at my code. The core of the code for calculating metrics has been encapsulated into this one function, which you could require. I actually didn't publish it as an NPM module because I did not think it was worth it. But anyway, given this function, you can feed it a piece of JavaScript code embedded in a string, and pass to this Halstead Metrics function, and it'll give you back a metrics object which looks like this. It's got colored code which can be, let me just run this guy actually. I have this example code right here. I'm going to run it. Show, not tell. Okay, so if you print out this guy, you get all of this. This color code looks really crazy. That's because it's got terminal coloring codes in it, with which you can do this. You can print out the colored code, and then you actually get the code colored. And the color coding scheme is such. All of the operands are colored green, and all of the operators are colored magenta. So the function keyword is an operator. The function name itself is also an operator. Triple equals is an operator. If is an operator. Else is an operator. That's another if. Return is an operator. A function call, so the name of the function itself is an operator, but this is the same operator as this one. So although the operator fib showed up 4 times, it actually within the unique operator set, fib only shows up 1 time, if that makes sense. But that's what the rest of the information shows. If you want to look into what the distinct operators are, I have used the ECMAScript set to collect all the distinct operators. And for this particular program, this Fibonacci program written in a recursive way, the distinct operators are these. The distinct operands are these. And then these arrays are all of the operators and all of the operands before the distinct operation was applied. Then, based on the calculations that we briefly went over in the Wikipedia page, I calculated these other metrics: vocabulary length, estimated length, line of code, volume, difficulty, and effort. Okay. And that's what we got. How does this code do it? Well, it does AST traversal, and if you're not familiar with AST traversal, I've actually been doing a lot of that lately, and you can actually find some of my videos in my programming language series or programming language playlist. Actually, I might you can actually find that on my website, tobyho.com, which contains, on the left hand side, it contains my video series, one of which is how to make a programming language. So at some point I start talking about making ASTs and evaluating ASTs and building a code generator. All of that has to do with AST traversal. So if you need an introduction to that, you can go there. But in this case, we're not making our own programming language. We're doing this AST analysis on JavaScript. And to do that, there are actually several very, very good, very high quality open source JavaScript parsers that you can install. One of them is called Acorn, and that's what I am using today. But there's also another one called Esprima, which was the first one that I learned. And it's 100% compatible with Acorn. So in my mind, they're interchangeable, actually. Acorn apparently is the faster of the two and is the more widely used at the moment. So that's why I'm using Acorn. But as far as the output of the parser is concerned, they're basically compatible with each other. I like to use the Esprima online demo to plug in arbitrary JavaScript and have it show me the AST that would be produced to see what it looks like and what I need to test against. I'm also using a library called ES-Traverse, which will allow you to write traversal code easier. It's a if you've seen a couple of my videos where I first wrote a recursive tree traversal algorithm and then I extracted a reusable version of that traversal function. That is basically what ES-Traverse is. And this is a freely available tool, also on NPM, that you can use. So you can say, given an AST, which you already got from using Acorn to parse your JavaScript code, you got the AST. Then you can feed it into ES-Traverse, and then you can either sort of register a listener, or not register, because this is not a register deregister kind of thing. You can either have this this is a visitor pattern, so I'm gonna call these guys visitor. So you can either have a visitor hook on the initial encounter of the node, or when it's leaving the node. Leave means it's already iterated all of your children and now it's coming back. Enter means I'm only encountering you now, but I haven't encountered any of your children. Okay, so if you want a pre-traversal, you set up a enter visitor. If you want a post-traversal, you set up a leave visitor. In my case, I wanted to use a leave visitor, and then inside the leave visitor, that's where I look at the nodes that I am seeing, that I'm traversing. So if it's a literal, which is either a string literal or a numeric literal, then I'm gonna say that's an operand. And this replace code allows me to color the code. Oh, I did do another video series on how to color code. I believe, yeah, that's here. You can it's called live code variable coloring by scope, and it's got 3 parts. Yes, so if you would like to dig more into that, you can go there as well. So this more or less does the same kind of thing, but also it's collecting operators and operands as we go, so that at the end we have collected all of the operators and operands. We do a distinct operator on them using the ECMAScript set, and then we have all those 4 numbers, and then we can derive all of these other numbers out of them. Okay, so given that, I also have a little run function, run script, which you can call to and pass in a JavaScript file, such as I have a couple of Fibonacci implementations, and then it'll do the analysis, color the code for you, and then it'll tell you how many total operands there are, how many distinct operands, how many total operators, distinct operators, the size of the program vocabulary, program length, estimated program length, lines of code. Lines of code is just how many lines there are here. So that's not actually a Halstead metric. The volume is, and the difficulty is, and the effort is as well. Okay, so then I made this thing, and then I decided to do an analysis of some code examples that I had in one of my articles. So one time I wrote this blog post, and where I wrote one word count example in 11 different versions. So I decided to basically do this analysis on all 11 versions of the code, and then basically try to see if I can learn anything from that. So this program, this FP comparison program, basically does that, and then it spits out the results in a CSV format, which then I import it into this Google spreadsheet, and this is what we have. So we had examples from 1 to 11, and I graphed the difficulty of each file from version 1 to 11. Versions 1 and 2 are actually imperative style programs, and versions 3 and 4 are object-oriented styles, and then the rest of the programs from version 5 to 11 are all programming functional programming styles, because this blog post centers on functional programming. So we have all of these are functional programming styles. These two are object-oriented style. These two are imperative styles. It actually seems like as we move on, sort of from the basic to the more advanced, the difficulty goes up, with the exception of the version 10 and version 11 of the functional programming styles. Version 10 drops off a little bit, and then version 11 goes up a little bit in terms of difficulty. In terms of vocabulary, you sort of see a similar trend, but not quite as dramatic. And when I looked at the profile of the length graph looks more or less like the difficulty graph, which makes sense, more or less. And I guess what that tells you is that most of the difficulty comes from the length. I mean, that kind of makes sense, but it doesn't give you too much more insight than that. Like if you tell me, like, the longer your program is, the harder it is to understand, I would have said, duh. So I don't really know what insight I can glean from that. So yeah, I should show some of the code examples. So one of the things is this. The example number 1 and 5 were seen as the least difficult. So I'll show you what they look like. So this is example number 5, which is written in an imperative style with a for loop, and then it tallies. And I actually agree. I mean, it's pretty simple, and it's meant to be very straightforward. Version 5 is what I call the functional programming, the softcore functional programming style, which means it incorporates map, filter, and reduce. So instead of written using a for loop, it uses map and reduce in 2 separate places. It also uses array.sort. So this one was actually seen to be slightly less difficult than the imperative, whereas the most difficult piece of code was version 9, which is the functional programming version where I just introduced currying. And when you use currying, you have a lot of these calls to the partial function, and the code does get longer. It's like we just have, so it's more wordy. Every single line I'm saying partial this, partial that. So I can see that, and then I have this crazy chained function call at the end here. So I can see that it increase because each one of these is seen as an operator. Each one of these function calls. Let me try to run FP examples. What was this? Version 09. So yeah, each one of these step functions was seen as an operator. So the number of operators you have gets bumped way up. And actually, let me plot this, the operator count. And whoops, the copy, paste. Okay, I'm gonna make a new graph that plots the operator count. My computer is also just the fan is just going crazy right now. So total, I actually want to see distinct operator count, although I'm not sure which one makes more sense. If you look at the difficulty calculation equation, it is actually the number of distinct operators is linearly going to impact the difficulty. So I think probably that one maybe is the one that's bumping it up for this program, because I had step 1, step 2, step 3, step 4. Yeah, I think that must be it. But the number of distinct operands is inversely proportional to the difficulty. This ratio is the number of total operands over the number of distinct operands. So you can think of it as the amount of repetitiveness of the operands. Operands, you can think of them as the variable names. So if you're repeating the same variable names a lot of times, Halstead thinks that makes the program more difficult to reason about because there's more repetition. Is he trying to like eliminate repetition? I'm not sure. By the way, the person who came up with this, his name is Maurice Howard Halstead, and he did it in 1977. He wanted to model software development. He called it software science. He wanted to model it sort of like the way you measure gases, and analogous to the gas equation. But surprisingly, it was incredibly hard to find his book. I tried looking up his book, and it's not sold anywhere. You might be able to get it used, maybe. Or not. It's not true that it's not sold anywhere. It's just I couldn't find an online version of it to read. I would have to buy it from Amazon, and it costs like $160 on Amazon, and I don't want to shell out that much money to buy this book. Okay, so I am actually, I mean, that equation seems dubious to me. But anyway, right now I actually want to plot the number of distinct operands. So let me do that. So the distinct, not operands, sorry, operators. So distinct operators. Did I do it? The number of distinct operators is here. Okay. There. Okay. So that is a plot now of the distinct operators. So 9 has the most distinct operators, and 4. So the number of distinct operators will like really impact the difficulty of a program according to this model. Let me bring these closer in, these charts. Yeah, according to this model, the length of the program, and also the number of operators, distinct operators you got in the program will really increase the difficulty of a file. Yeah, so I would say at this point I was not really able to, I mean, other than that, I mean, I guess those two things sort of intuitively make sense, but I don't feel like that I've got a great insight from that. Those things seem obvious to me. One thing though I would say I really like about the Halstead metrics is that it has a concept of vocabulary size, and I think that that's a important concept to keep in mind when you're writing code. Is the vocabulary I'm using? Am I using a very large vocabulary or very advanced vocabulary, or perhaps am I inventing a lot of vocabulary into my code that readers of my code would have to know before they can even comprehend my code? Each new vocabulary that you introduce into the code needs to be learned, and that's a cost that's embedded in new vocabulary. And I think for authors of code, you should keep that in mind when you're thinking about your code from the perspective of the reviewer of your code. I I find the difficulty measure kind of unintuitive, and I don't really know what insight I am able to get out of this. I think the length measure makes sense. The length measure is simply the total number of operators plus total number of operands, which the entire program consists of operands and operators, really. Every sort of symbol in the program can be categorized either as an operator or an operand. It makes sense the length of the program should correspond to their sum. So, I mean, another metric for measuring length is just lines of code, and I can see that that metric is not as detailed as this one. So I guess that is something, but you're just measuring the length of the code at that point. So after having done this whole exercise, I don't feel super excited about Halstead metrics at this point. But I did want to present you with that information. So yeah, that's what I got, and hope you enjoyed that. And yeah, I'll see you soon.